Hey guys, welcome back to another video. This time I'm basically filling in all of the gaps from my GCSE science videos. I'm going through all of the different past papers that have ever come up to help you with your revision, where I'll go through, show you exactly what the examiner is looking for when they mark your papers, and also show you how you can get the full marks, any common mistakes that people make, etc, etc. This time we're looking at, again, combined science for now. We'll do triple science a bit later, but 2023 chemistry paper 1. And yeah, like I said, we'll just get straight into it with the first question. This question is about carbon dioxide. Carbon dioxide is soluble in water. When something's soluble, it means it dissolves. So if it's soluble in water, it means carbon dioxide can dissolve in water and forms an acidic solution. Which ion makes the solution acidic? So you can either say hydrogen ions or you can say H plus ions. I think H plus is slightly more accurate if you were to ask my opinion. And remember, for alkali, it's OH minus. This is name an indicator, so any indicator that can be used to test if the solution is acidic and give the result. Probably the most common one is universal indicator, which would turn from like green, because water is normally neutral, and it would go to a red or orange or yellow, depending on how acidic the solution is. But you can also say, for example, blue litmus paper, which would turn red in an acidic solution, and methyl orange, which also turns red in an acidic solution. So any of those three would give you the marks. Figure 1 shows the mass of carbon dioxide that will dissolve in 1 decimeter cubed of water at different temperatures. And as you can see, it's kind of decreasing over time. The mass of carbon dioxide dissolved in the water decreases as temperature goes up. So how does the solubility of carbon dioxide change as the temperature of water increases? Remember, solubility is how easy or how much carbon dioxide can dissolve in water. So as this is decreasing as the temperature goes up, then that means the solubility should decrease as temperature increases. Carbon dioxide dissolves in water to form an acidic solution. How does the pH of the solution change as the temperature of the water increases? So let's think about this for a second. If we go back to that, here, because the mass of carbon dioxide dissolved is decreasing as temperature increases, that means the amount of carbon dioxide in the water is decreasing, right? Now, carbon dioxide causes it to be acidic, so more CO2 means it's going to be more acidic, right? That's what it's telling me here, which means if I'm decreasing the amount of CO2, that means I'm decreasing how acidic the solution is. Now, if you remember, with a pH scale where you have 1, 2, 3, 4, up to 7, and then it keeps going up, right? This side is alkali, and this side is acidic. So when we're getting more acidic, the pH is decreasing, which means in this case, because the acidity is decreasing, the number should get bigger, which means the pH of the solution should increase because it heads towards neutral. Okay, so just be wary of that. They're trying to trick you with the wording. Calcium carbonate reacts with hydrochloric acid to produce CO2. This is the equation. So calcium carbonate plus hydrochloric acid produces calcium chloride, carbon dioxide, and water. What is the state symbol X in the equation? Well, some of you might just say, well, it's water, so it's obviously a liquid. But bear in mind, it could produce ice, it could produce steam as well. But if we have a look at this letter over here, this is aqueous, AQ. Aqueous means that the calcium carbonate is dissolved in water. Now, you can't dissolve something in ice or steam, which means H2O has to be a liquid. So again, if it ever says aqueous, it means that the water has to be a liquid because it's got something dissolved in it. So it looks like we're going to have a 6 marker in a second. There's a set of equipment used for an investigation. We have a conical flask, we have a mass balance, a gas syringe, and a measuring cylinder. And the student investigated the volume of CO2 produced when different masses of calcium carbonate react with hydrochloric acid. Describe the method. So when I'm looking at this, I need to break it down. It says different masses of calcium carbonate. So that's going to be our independent variable, right? That's what we're changing. We're going to put different amounts of calcium carbonate. And it's reacting with hydrochloric acid. Now we want to use the same concentration and volume of hydrochloric acid, and we want there to be enough hydrochloric acid to actually fully react with all of the calcium carbonate. So the independent variable is the mass of calcium carbonate. That's what we're going to change. The volume of CO2 is our dependent variable, so that's what we're going to have to measure. So if we look back at what we have here, well, we have a mass balance to measure the mass of calcium carbonate. That would give us a mark. So use the mass balance to measure 5 grams of calcium carbonate, and then every time you repeat the experiment, add an additional 5 grams. So 5, 10, 15, 20, as an example. How do we measure the volume of gas? Well, we don't use this, right, a measuring cylinder. That's going to be for the hydrochloric acid. This is where we're going to react the reactants. It's the gas syringe. So this little bung here goes on top of the conical flask, so it blocks anything from escaping. The gas will enter the syringe and push this syringe part out up into a certain volume. The reason why it's important to do that, and again, if you guys are planning on taking an A-level science, biology, chemistry, or physics, you have to do similar things to this, and it might be with an experiment you've never seen before. So it's very important for you to kind of break down what is the independent, what is the dependent, and what are the control variables, so you can state them and get quite a few marks. It's also just good science anyway. So let's see, what's the first step? Well, what we're going to do is we're going to measure a certain mass. So we say measure, let's say 10 grams of calcium carbonate. It doesn't really matter what you say, to be honest, using a mass balance. That right there is 2 bullet points in the mark scheme, because again, we've stated the equipment we're using and we're stating what we're doing with it. So I'm not going to say it's worth 2 marks necessarily, but it is 2 points that the examiners are looking for. I'm going to actually go down a little bit more. What do we do next? Then what we're going to do is we're going to place calcium carbonate, let's be specific, into the conical flask. We're going to measure a volume of hydrochloric acid. Again, this can be anything, but we want it to be in excess, right? The reason why I say that is what we don't want happening is not all of the calcium carbonate reacts with hydrochloric acid, because then we've added another variable, right? We've got some leftover calcium carbonate that hasn't produced CO2, so that's going to skew our results a bit. So we want to make sure it's a lot. You can state something for this, like 50 centimeters cubed or something crazy. You don't have to. Then we're going to add the HCl to the conical flask and immediately place the rubber bung of the gas syringe over the flask. The next thing that's really important, in fact, it doesn't say the rate, right? No, it just says the amount of the volume of carbon dioxide produced. The important thing here is, how long do you wait? Now again, you want to wait a sufficient amount of time for the reaction to finish. And it also has to be the same amount of time every single time. Because let's say you wait 10 minutes and that isn't long enough for the whole reaction to happen. If you wait 10 minutes every single time, at least then you're not, skewing the data at all. So let's write that. I'm going to say wait. You can say a sufficient amount of time, but let's say wait 10 minutes and record the total volume of CO2. Cool. Actually, in the gas syringe, we should probably specify that. Then all you're going to do is repeat with different masses of calcium carbonate. There you go. That's 6 marks. Nice and easy. Perfect. That's all you have to do. Okay. Lithium hydroxide reacts with sulfuric acid to produce lithium sulfate. The equation for the reaction is this. What type of reaction? Now, this can be slightly tricky for some students to figure out, for anyone to figure out really, not just students. But here's how we can kind of work it out. We've got an acid reacting with something. Now, an acid and a hydroxide always produces water, but let's say you didn't know that. It also produces water. So let's put this together again. We have an acid reacting with something, and it produces something that isn't an acid, because lithium sulfate's not an acid, and it produces water. That will always be a neutralization reaction, because we've neutralized it, right? There's no longer an acid present, which means the pH has gone back to 7. So again, we have an acid reacting with something which produces not an acid and water. It has to be a neutralization reaction. And then for part 2, calculate the relative formula mass of sulfuric acid. Relative formula mass is really, really easy to calculate. We're literally just going to have a look at all of these different atoms that we have and add up their atomic masses. So for example, with hydrogen, well, we have 2 hydrogens, right? So that's going to be 2 times 1, which is 2. With sulfur, we only have 1, so it's just going to be, if you want, you could write 32 times 1 if you really wanted to, which is 32. And with oxygen, we have 4, so we're going to have 16 times 4, which is 64. And then all we're doing is we're adding all of those together, nice and easy. So that would be 96, 98 for that one. There you go. Not too bad. So again, relative formula mass is literally just all of the atomic masses added together. Not too bad. This is also a really, really nice calculation. Remember when we go back to here, the reason why I had 16 times 4 is because I have O4, so I have 4 oxygen atoms in this molecule. Here I have 2 hydrogens, and that's why we have that. In fact, I probably should put an O4 there, but that's okay. Now, this sounds like a really complicated calculation, right? Calculate the percentage by mass of oxygen in lithium sulfate. So percentage by mass means we're going to work out the mass of the oxygen as a percentage of the mass of the entire molecule. So in other words, the mass of these O4 as a percentage out of 110. That's all they mean. So all we need to do is work out the mass of O4, which we've already worked out before, but let's do it again. 64. And now we're going to make this a percentage out of 110. That's what percentage by mass means. So we have 64 out of 110 multiplied by 100. And you know what, don't even stress yourself. All of these are calculator papers, so let's just get our calculators out. 64 out of 110 times by 100, and we get 58.2%. In fact, oh no, it says 2 significant figures, never mind. I was checking if there was any there. So 58%. In fact, over here I'm going to write 58.18%, so then they can see that we've rounded. For 4 marks, that is a beautiful question. I love calculations in science. And again, one more calculation. This time it's a unit conversion. A solution contains 0.3 grams of lithium sulfate in 25 centimeters cubed, but they want the concentration in grams per decimeter cubed. Now, concentration normally is just the mass over volume, so it is just going to be 0.3 divided by 25, but they've said they want it in decimeters cubed. Now, the question is, how do we go from centimeters to decimeters? Well, 1 decimeter is equal to 10 centimeters. So in other words, to go from decimeter to centimeter, I times by 10, which means if I want to go from centimeter to decimeter, I divide by 10. Now, here's where people get confused, is because it's centimeters cubed instead of just centimeters and decimeters. Now, I'm going to show you something which is hopefully fairly useful to you. But logically speaking, actually no, I'm not going to do that. To go from decimeters to centimeters, we times by 10. But if you notice, we have decimeters cubed to centimeters cubed, which means we times by 10 cubed. And that means to go from centimeters cubed to decimeter cubed, we divide by 10 cubed. So a lot of students try and memorize all the different conversions, like, oh, times by 1,000, times by 10,000, or divide by the whatever. You don't need to worry about that. Instead, decimeter to centimeter, just remember that one. That's times by 10. So if it's decimeter cubed to centimeter cubed, you times by 10 cubed. If it's decimeter squared to centimeter squared, you times by 10 squared. You don't need to memorize all the different conversions. So to go from centimeters cubed to decimeters cubed, I'm dividing by 10 cubed or dividing by 1,000. So 25 divided by 1,000, 0.025, which means the concentration is just 0.3 over 0.025, which I'm pretty sure is going to be 12, right? Because you're going to times it by... Well, you know what, let's just see. Let's not speculate. Look at that. There you go. For 3 marks, not too bad, but again, those conversions are a little bit tricky to remember, so just remember the centimeter decimeter conversion, and then square it or cube it as you need it. Sodium is in group 1 of the periodic table. Sodium reacts with oxygen to produce sodium oxide, balance the equation. For balancing equations, again, people find it a little bit tricky. Something that you can do is just basically count the atoms on both sides. So for example, if we start with sodium, on the left side at the moment we have 1, but on the right side we have 2. So to fix that, we're going to shove a 2 in front of the sodium, right? Just to start with. Now we do have 2 on both sides. Now if we do the oxygen next, we have 2 on the left and we have 1 on the right. So I need to put 2 in front of there. But now we have 4 sodiums on the right and only 2 on the left. So how do we fix that? We just change that to a 4. And now you can see that we have 4 sodiums on the left, 4 sodiums on the right. Don't forget Na2 means that there's 2 sodiums. So 2 times that we have 4. So we have 2 lots of 2 sodiums and an oxygen. And we have 2 oxygens and 2 oxygens on the right. Now, explaining what happens to sodium and oxygen atoms when sodium reacts with oxygen in terms of electrons. So here they've told us that sodium is in group 1 of the periodic table. That means that it has 1 electron in its outer shell. Now, how many electrons can fit in an outer shell? Okay, except for the inner shell anyway, as in the very first one. Well, normally it's 8. Okay? Now, that means, and don't forget, an atom really would like to have a full outer shell. Okay, so if you imagine this, it has 1 electron in its outer shell. So let's just say for sodium, by the way, this isn't exactly what sodium looks like. So it has, let's say, and then we also have just 1 on the outside. Now again, so we can either get 7 more electrons from somewhere, or it could just give away that 1 electron, right? Because then it has a full outer shell on the inside. So what's easier, do you think? Gaining 7 electrons or losing 1 electron? Well, the easiest thing would be losing an electron. That's the process of ionic bonding. Okay? So again, atoms would like to have a full outer shell. So they can either lose or gain electrons, or they can share if they have roughly 4 electrons. But for the most part, because this is so extreme where there's only 1 electron in the outer shell, it just wants to get rid of that electron. It'd be so much easier if they just got rid of it. Now they've told us it reacts with oxygen. Oxygen, without even looking at the periodic table, is going to be in group 7. Now what does that mean? It means it has 7 electrons in the outer shell. And remember, they want to have a full outer shell. So, oxygen can either gain 1 electron, or it can lose 7 electrons. And once again, which one do you think is easier? Well, definitely gaining 1 electron, right? Because you can find an electron more easily than you can just get rid of 7. So, here's the beauty of it, right? Sodium has an electron it wants to get rid of. Oxygen has an electron that it really wants to have. So sodium will give an electron to oxygen, forming an ionic bond, because there'll be a sodium +1 ion and there'll be a oxygen -1 ion. Why positive and negative? Well, think of this. Sodium is currently neutral. If it gets rid of a negative charge, it means it's positive, right? You know, we're taking away a negative, so it becomes positive, right? Likewise, electrons. Oxygen is neutral. It's gaining a negative charge, so it's going to be -1. That is, broadly speaking, what happens when sodium and oxygen react to form sodium oxide. So let's type that up now. So the first thing is that the sodium atom will lose 1 electron, and the oxygen atom will gain, in this case, 2 electrons, right? And again, the reason for that, bear in mind, is because it's 2 sodiums to any single oxygen. So actually oxygen is in group 6, isn't it? Whoops. Again, either way, it's the same. It's the same concept anyway. So again, that'd be either +2 electrons or -5 electrons. And again, that's completely fine. But again, looking at the periodic table, if it's in group 6, it either wants to gain 2 electrons or lose 6. Or you can tell it from the chemical formula here, right? We'll gain 2 electrons. This gives us a ratio of two sodium atoms bonding to one oxygen atom. And now you need to talk about the actual ions. That's the fourth mark, so mentioning any of the ions. So you can either say forming Na plus ions, or forming an O2 minus ion, or to say to have ions with full outer shell, something along those lines. But you need to mention the word ions in order to get the marks for ionic bonding, shockingly. So we have sodium burning in oxygen. Two observations. When you're talking about something burning, the first observation should be the color of the flame, because that's very, very important. With sodium, it burns either yellow or orange. They accept either because it's basically the same thing. And then the other thing you can talk about is what actually happens to the ball itself. So you can say sodium melts, for example, because it has a very low melting point. Or you can say that it produces white smoke or something along those lines. But bear in mind that not all metals produce a white smoke, so just be careful with that. And it's to describe two differences in the observations if potassium was used instead of sodium. So again, you want to talk about the color of the flame, because that's something very obvious. That's how you can tell what's burning at any given point. So this is with a lilac flame. So like purple. Oh, I didn't write flame for this. I should have written flame. And another kind of observation is because it reacts faster, it's going to burn faster. Or you can say more vigorous if you'd like. Also, something fairly interesting is you can kind of cheat this one. If you can't remember which color it burns with, you can just write burns with a different color flame, because that is an observation, and you can actually get the mark for that, which is quite funny. Okay, so we have halogens, and they contain protons, neutrons, and electrons, just like all atoms. What is the order of discovery of the proton, neutron, and electron? Now, the only thing you really need to know to really eliminate these options is the neutron was last. Do you see? Detecting uncharged particles is extremely difficult, whereas detecting charged ones isn't that bad. So now all we have to do is decide between the second and the last one, which is really useful, right? We've doubled our chances of guessing it correctly. Just so you know, it's a bit weird because you would expect maybe proton to be first because it's heavier, it's bigger, so you might be able to see it better, but in fact it was actually the electron that came first. So it's electron, proton, and then neutron. That's just it. Then we have the mass of a proton and an electron. Calculate how many times heavier a proton is than an electron. So that means it's proton divided by electron, because proton comes first. So we're just dividing those two numbers. We should probably write down the calculation we're going to put on our calculator, just because we can kind of guarantee that we at least get a method mark in case something weird happens with our calculator. Some students' calculators are a bit cheaply made and they just don't give the right answer sometimes, especially with standard form. Maybe you enter it a bit wrong. God knows what happens, right? So all we need to do is shove this in after we've written down our calculation. So we've got that method mark regardless of what happens. And then assuming we get this right, we get this. So 1836.64. It doesn't tell me to what significant place or anything. So I'm just going to round it to the nearest whole number. So 1837. And there you go, for 2 marks, not too shabby. A bromine atom can be represented as 8135 Br. What is the number of neutrons? So here, the 35 represents the proton number. That's the number of protons, and it's also the number of electrons, okay? So it's 35 protons, 35 electrons. 81 is the mass number. It's the number of proteins plus the number of neutrons. So what we're going to do is, we know that there's 35 protons, so we're going to do 81, take away 35, to get just the number of neutrons, which is 46. Well, it's a calculator paper, by the way. Then it says, what is the number of electrons in a bromide ion? Now, we're talking about halogens here, but let's say you weren't too sure. Remember, you have access to a periodic table in your exam. Don't be afraid to use it. Bromine is over here. It is in group 7. Remember what I said in the last question, right? Group 7 means in its outer shell we have 7 electrons. And how many electrons would it like to have? It would like to have 8. So it can either get rid of 7 or it can gain 1. It's far easier to gain 1 electron than it is to lose 7. And so we are going to basically add 1 electron to this. So when it says what is the number of electrons in a bromide ion, well, it's not 35. There's 35 electrons originally, but it's going to gain 1 electron to become an ion to have a full outer shell. So it's going to have 36 electrons in its outer shell. The periodic table has almost everything you need to know when it comes to bonding and ions and everything like that. Okay, so percentage abundance and then calculating relative atomic mass. There's a bunch of different ways to do this, so I'm going to try and just explain to you how you do it. I'm not going to give you like a formula or an equation because I don't think that really helps you understand like how much it is. Because there are different isotopes of chlorine, it means that the relative atomic mass has to be like a mixture of these two numbers. So it's going to be somewhere between 35 and 37. So again, here the mass number of chlorine is 35, here the mass number of chlorine is 37. Because they have different abundances, and abundance is just how common they are. So if I were to take a chlorine atom, just a random chlorine atom, 75.77% of them are chlorine 35, 24% of them are chlorine 37. So in other words, I have a 75% chance of getting chlorine 35, a 24% chance of getting chlorine 37. And so when I take if I take a lot of chlorine atoms, trillions and trillions of chlorine atoms, their mass isn't going to be 35 or 37, it's going to be somewhere in between, because 3/4 of them, 75% of them, are chlorine 35, and 24% of them are chlorine 37. So that's what we're trying to work out, is what the relative atomic mass is. So what's the average mass of these? So the way I do it is I just take 75.77% of 35, which, by the way, you could just use as a multiplier, right? 0.7577 times 35. And then we're going to add 0.24, 24.23% of 37. And that's it. Now, the formula you might have seen before is something along these lines, where you have 35 times 75.77 plus 37 times 24.23 all over 100. Now, if you actually compare that to what I'm doing, it's the same thing. I've just divided by 100 first because I'm taking a percentage of a number, like we do in maths. So when you take a percentage of a number, you make it a multiplier, right? Or you enter it in your calculator. Like, you can actually enter percentage of amount in your calculator. You could do 75.77% of 35, and I get this. If I do 0 point instead, I get the exact same number. It's the same thing. Again, if you want to do chemistry at A level, it's good to have an understanding of why you're doing something rather than just remembering a formula. But anyways, once we add those together, we'll get our number. Now, I should be able to actually not use brackets here. But let's see. 35.556. Yeah, we could do that. Is that okay? Yeah, so what should we round it to? It says 2 decimal places. 35.56, let's call it. And yeah, that would probably be the best thing. Actually, I've just realised that number doesn't look the same as this. 35.48. Okay. Oh, I didn't know I could rub out like that. That's perfect. But again, try and make sure you understand what the calculation is telling you rather than just memorising it. So for this question, we have the outer shell in a molecule of chlorine 2. Complete the dot and cross diagram. So again, let's whip out our periodic table. Chlorine is in group 7, which means it has 7 electrons in its outer shell. So again, it needs to either gain 1 electron or do 7. Now, because these overlap, this is a covalent bond, which means they're going to share an electron. Now, how many electrons do they need? Well, they need 1 electron each, which means they're probably going to share 1 electron. Logically, right? And that made that have a full outer shell. Perfect. Now, how many more electrons do we need? Well, there's 7 in the outer shell. So the one on the left, I'm going to say this one is the one with the crosses. It's going to have 6 more. So 1, 2, 3, 4, 5, 6. The one on the right should also have 2, 3, 4, 5, 6. So now, if I cover up the left-hand side for a second, I was about to do that with my hand, which is stupid. If I look at just this one on the left, how many electrons does it have? Well, it has 1, 2, 3, 4, 5, 6, 7, plus the dot, 8. And if I look at just the one on the right, it has 7 dots and a cross, so it has 8 as well. So it's nice and happy in a covalent bond with another version of itself. During electrolysis, ions are discharged at the electrodes to produce elements. A student investigates the electrolysis of sodium chloride. Why does sodium chloride not conduct electricity? Well, if something doesn't conduct electricity, it's always the same reason. Okay? It's because it has no free ions, technically no free electrons for a lot of cases, but also just no free ions. So if you want to be really general and you want to definitely get the mark, always say ions. Okay? So again, if something doesn't conduct electricity, it's because its structure doesn't have free ions. Always. Which means there can be no movement of charge. Movement of charge is current, which is electricity. Sodium chloride solution conducts electricity, so when it's dissolved. Complete the sentence. Sodium chloride also conducts electricity when it is a liquid, or you can say molten. Remember, molten and liquid mean the same thing. A molten substance is just a liquid that's really hot. So for example, like if it's a rock or a metal traditionally, then when you melt it becomes molten, but it is just a liquid. Figure 5 shows the apparatus for the electrolysis of sodium chloride. So we have a positive and negative electrode, all that stuff. It says inert electrodes. Suggest an element that can be used to make the inert electrodes. Again, the key thing here is when they're inert, it means that they are not going to react. Okay, so we're not producing anything else, because that kind of defeats the purpose of separating something if you're just going to bond it to something else. The common one is carbon. You can also say graphite, but graphite is made out of carbon, so potato, potato. But also you're allowed to say any other kind of non-reactive substance like platinum, gold, or silver. But again, carbon or graphite is the most common because it's far cheaper than having platinum electrodes. And then lastly, complete the half equation for the production of chlorine at the positive electrode. So we have Cl minus. Now remember, it's producing Cl2, so I know one of the products on this side is Cl2, right? I know that because it's telling me. Now, what has to happen? Well, this is neutral. Okay? Well, actually, no, before we even say that, we have 2 chlorines here, we only have 1 chlorine there, so stick a 2 in front. Now it's balanced, right? The 2 chlorine negatives become 2 chlorine neutrals, okay? Now, what else has to happen? How does it go from a negative ion to a completely neutral molecule? Well, what's causing the negative? It's an electron, right? So that means those 2 electrons, those 2 charges have to be somewhere, and they're over there. 2 electrons. So again, when you're doing half equations, when you're doing any equations really, the atoms have to be balanced. So if there's 1 chlorine on this side, there should be 1 on the other side. If there's 2, there should be 2, and so on. But also the charge has to be balanced. If there's 2 negative here, and there's just a neutral here, there has to be something giving the 2 other negative charges. Okay, so here we have to explain these 2 observations during the electrolysis of sodium chloride. It normally has a pH of 7. Now we have to explain why hydrogen gas is produced at the negative electrode, specifically the negative, and why the pH of the solution increases. Remember from the earlier question that a higher pH means it's going above 7, which means it's becoming more alkaline, which means the number of OH minus ions is increasing. So let's get started. So the first things first is what happens during the electrolysis. Well, the water breaks down, so H2O breaks down into H plus and OH minus ions. Since H plus ions are positively charged, the H plus ions are attracted to the negative electrode, okay? Where they'll then, reduce, which are then reduced, forming hydrogen gas. So that explains the hydrogen gas. So why is the pH of the solution increasing? Well, that means that the number of H plus ions decreases, but the number of OH minus ions, stays the same, right? Because they're not reacting. So that means, relatively speaking, there are more OH minus ions, which means we're increasing the alkalineness, the pH of the solution, which increases the pH of the solution. And that's it. Because there's a relative increase in the number of OH minus ions. Because the OH minus ions stay, H plus ions going away, so there's less acid, there's the same amount of alkali, so it's as if it's becoming more alkali. So here we have acid reacting with some metals producing soluble salts, soluble meaning that they can be dissolved. As soon adds magnesium to HCl until no more acid reacts and excess magnesium remains. As we have a solid magnesium left over. Describe how solid magnesium chloride, so this stuff, is obtained from the reaction mixture. Well, the first thing you need to do is you need to filter to remove the excess magnesium. Remember, now, how do you know if you need to kind of filter versus crystallize versus whatever? Well, remember, the magnesium is a solid. So to remove solids out of something, you filter it. You can't remove aqueous stuff by filtering because it's dissolved, okay? So how do we actually remove this? Then all you need to do is either evaporate the water. So you can either evaporate water, because that will leave behind magnesium chloride. Again, the experiment that you can try at home is dissolve some salt in water. Even if you filter it, it's still salty water. However, if you boil away the water, you're left with salt in the bottom of the glass. Or you can undergo a crystallization reaction. Crystallization reaction. It's up to you which one you want to do. The reaction between magnesium and hydrochloric acid is a redox reaction. Explain what happens to magnesium atoms in this reaction. So again, you don't have to use the periodic table for this one, but it might be a good idea. If we go to magnesium quickly, magnesium is here, it's in group 2. That means there's 2 electrons in the outer shell. That means it wants to get rid of 2 electrons because it's easier to lose 2 electrons than gain 6 electrons. So it's going to be losing electrons. Okay, now if you remember from oil rig, oxidation is loss, reduction is gain. So if we're talking about electrons when we say loss and gain. So that means magnesium is oxidized because it loses 2 electrons. That's it. So because it's a redox reaction, you want to find which one's reduced, which one's oxidized. Use the periodic table to help you. It is there for a reason. And again, it's oxidized when you lose electrons, reduction when you gain electrons. Here we have a 6-mark calculation which involves moles and concentration and all of that fun stuff. It says 0.72 grams of magnesium is added to 100 centimeters cubed of hydrochloric acid. Hydrochloric acid is in excess. Calculate the concentration of magnesium chloride solution produced in grams per decimeter cubed. So to work that out, we're going to be using the mole equation, which is mass over formula mass or atomic mass, depending on what you're dealing with. And in order to work out the concentration, we need to do mass over volume. So we need the mass of magnesium chloride as well as the volume of magnesium chloride. Now to work out the mass, well, you can't work out the mass easily. Instead, we're going to use moles. So we're going to work out the moles of magnesium chloride, then use this equation to work out the mass. So the first thing we need to do is how can we work out the number of moles of anything? Well, remember, the numbers in front of these chemicals here tell us how many sets of moles we need, okay? So it tells us what ratio we're mixing these things in. So if I work out the moles of magnesium just by itself, because the number in front of these is both the same, it's both 1, that means the number of moles of magnesium is the exact same as the number of moles of magnesium chloride. So that's really handy. So instead, I'm going to work out the moles of magnesium. Remember, the number of moles is equal to the mass, which is 0.72 grams, divided by the formula mass or atomic mass, which in this case is 24. So let's do that quickly. This has already given me some marks. In fact, 1 mark. No, 2 marks for getting the correct number of moles. Which means, again, for MgCl2, the moles is also equal to 0.03. So if I want the mass now, I can rearrange this formula. So the mass is going to be the number of moles times mR. So the number of moles is 0.03. It's the same because, again, the numbers in front of the chemicals is the same. So, for example, with HCl, there'd be 2 times the number of moles. So it'd be 0.06 instead of 0.03. And we have MgCl2, and it gives us the formula mass. How beautiful. We don't have to work it out. Although working out isn't too bad. You can do that from the periodic table. And we get 2.85 moles of... grams of magnesium chloride. Now, when it says here, calculate the concentration in the solution produced. Now, the solution produced means that it's going to have the exact same volume of hydrochloric acid, because remember, this magnesium is being dissolved in 100 centimeters cubed. So the solution left over will also be of a volume of 100 centimeters cubed, but they want it in decimeters cubed. So remember what we said, right? To go from centimeters to decimeters, we divide by 10. So going from centimeters cubed to decimeters cubed, we divide by 10 cubed. So we're going to do, what was it, 100? Yeah, 100 divided by 10 cubed, which is 100 divided by 1,000, which is 0.1, which means our concentration finally is 2.85 over 0.1, which is 28.5 grams per decimeter cubed for 6 marks, which is beautiful. Really nice. Last question finally, it's all about structures, as it says here. Which pair of substances both contain atoms in hexagonal rings? So we have diamond and graphite, fullerenes and graphene, nanotubes and silica. The answer is fullerenes and graphene. Again, these are just structures you need to know. There's not really a trick to remember them. I mean, there might well be, but not that I'm aware. And then it says, explain why the structure of copper allows for the conduction of thermal electricity. It's actually the same as the reason why it can conduct electrons, in other words, electricity. So funnily enough, if something's a really good conductor of heat, it's actually a really good conductor of electricity a lot of the time, which is quite nice. And it's all because of those juicy delocalized electrons. So copper contains delocalized electrons. Remember, delocalized means that they can move throughout the whole structure. So an electron on one side of a copper tube can move all the way to the other side, completely fine. These move through the structure, transferring energy along the copper, which again, energy in this case is your thermal energy. Explain why copper oxide has a high melting point. So when things have a high melting point, what does it mean? It means the intermolecular forces, i.e. the forces between the molecules inside copper oxide, are very strong. Now, how do we describe that? Well, copper oxide is, of course, a metallic structure, an ionic structure, because it's a copper and an oxygen. So what we have here is you have strong forces of attraction between oppositely charged ions, right? The copper and the oxygen have opposite charges, which means they are very strongly attracted. The electrostatic force of attraction is the strongest force that you're going to encounter in a structure like this. So again, as in between the molecules. That gives you 2 marks, by the way, because the strong force of attraction is 1 mark. That's why it has a high melting point. But what causes the strong forces of attraction? The oppositely charged ions. What does this mean? It means a large amount of energy is required to break the strong intermolecular forces. Okay? And again, it's between the molecules. Again, we're not trying to separate copper and oxygen. We're trying to separate different copper oxides from each other. And then from there, we have to explain why water has a low melting point. Well, this is very, very similar to this, except you're saying basically the opposite. So first thing is that there are, by the way, there's a lot of different things you can say. There are weak intermolecular forces of attraction. Why is that? Well, you can say a few different things. It's because it has a simple molecular structure due to a simple or small molecular structure. It's one thing, right? It's just hydrogen and 2 oxygens floating around separately. And what does this mean? Well, again, like I said, it's the opposite of this, right? So strong forces of attraction, we said weak forces of attraction, large amounts of energy, Therefore, there's a low amount of energy required to overcome, to break into molecular bonds. And that's it. We're finally done. Chemistry paper 1, very exciting. And again, if you found this very useful at all, then please do consider subscribing. I'm also going through all of the GCSE maths papers, as well as the A-level maths papers for you guys in the future. If you would like to join any of the tuition classes, then again, in the description there's my email address and also my website in case you want more information. But other than that, I'll see you in the next one.